right, so in this chapter, we're going to take a look at once again, thermochemistry. In this chapter, we're going to learn a lot. We're going to learn about the difference between temperature and heat. We're going to learn that, hey, everything has to have a temperature. But we're going to find out that you don't always have to have heat in this case. So we'll learn about energy. We'll learn about the first law of thermodynamics. We'll talk about this thing known as calorimetry. We'll talk about the enthalpy of reactions. We'll talk about enthalpy, what enthalpy happens to be itself. Hess's law. Wait until you get to Hess's law. You're going to like this. This one is actually a puzzle. Most students love this. Even in the AP, they love these sort of Hess's law problems because it's just really easy to work with. We'll talk about enthalpy of formation. That's a pretty easy one as well. And we'll talk a little bit about the difference between the unit of calories that we use in this classroom versus the actual food calories. So we'll talk about all this good stuff. So, getting started. Before we even get started, matter of fact, before we get started, temperature. Since we got our test tomorrow, temperature is a measurement of what? Average kinetic energy. So just keep that in mind. Temperature is a measurement of average kinetic energy. So we're going to see how temperature, once again, is different from heat. So we're going to take a look at a second, energy versus heat. And then we'll talk about eventually what's known as the heat capacity and the specific heat capacity. So the first thing we need to talk about is just thermochemistry in general. That definition, thermo of course means heat, and then we got our chemistry here. And what thermochemistry is concerned with is it's really concerned with the transfer of energy that's going to occur in either a chemical reaction or it can be a physical process. And the sort of physical process that we're going to be looking at in this class is going to be phase changes. Like going from a solid to a liquid, melting, or maybe going from a liquid to a gas. So we're just going to look at those phase changes and kind of look at how the energy is being transferred. Now, when we talk about energy, back in conceptual physics, you learn that energy comes in two forms. You can use the energy to do work, or the energy is going to come in the supply of heat. So those are kind of the forms in which you're going to find the energy. And keep in mind that when it comes to energy, there is that law that says the law of conservation of energy. Energy can neither be created nor destroyed, which means that all we have within this universe with regards to energy is all we'll have. Even if we think about it from the perspective of the sun, we can 100% account for all of its energy. Because one of the things I know is that all that energy that comes into our atmosphere for the sun, I can account for all of it. Some of that energy is going to go in and it's going to cause the air molecules to start to speed up. Their average kinetic energy is going to start to move. So some of the energy is going to warm those molecules up. Some of that energy is going to hit the Earth's crust. It's going to warm the Earth's crust. Some of it's going to hit us. We're like, oh, it feels so warm. We're taking in the energy. Even when you think about plants, plants are going to be like, you know what? We'll use a little bit of it to warm us up, but it's going to take a lot of it and use what process is going to go through with that energy? Photosynthesis. And of course, when it takes it, it's going to say, hey, I'm taking that energy and I'm storing it, right? In the form of glucose. That glucose at that moment in time, technically, that glucose is not doing work and it's not supplying heat. There's really one other place in which you're going to find the energy. And that's going to be in the form of what? It's potential stored energy in this case. It's stored within the glucose. But at the same time, we'll come around and pick the plant up and we'll eat the plant. When we eat the plant, then we're going to take that glucose and we're going to start doing things such as work. Hey, look, took the graduated cylinder and wait a second, work. Work from conceptual physics was defined as the amount of force times what? Distance, exactly. So me using force to lift this thing up a certain distance, I'm doing a certain amount of work in this case. At the same time, when I consume that plant and that glucose is being used, I can put it to work. I can use it in the form of, hey, wait a second. From the plant's perspective, it's photosynthesis. But when we take the glucose and we go in the opposite direction, we call that thing, we talked about it. It's cellular respiration in this case. And we're now going to end up, wait a second. Cellular respiration is also AKA one of the 5 reactions that we learned in this classroom. Which reaction is it? Combustion reaction. Combustion reactions are notorious for producing what? Carbon dioxide, water, and also heat. Which means that when it comes to the actual glucose that we take in, we can do work with it, We got heat coming off of it. We eat too much of the plants, and guess what's going to end up happening? What is our body stored as?
Fat.
That's fat. And then it's just potential energy. It's not gone, it's there. Eventually, hey, maybe my body might tap into that energy to actually use in this case. Only thing I'm pointing out is law of conservation energy shows that all the energy is being conserved. Here we go. So once again, what we're going to focus on is just heat. But before we go there, I just want to talk really quickly about the units that we'll be using to represent energy and also heat. And if you remember, the famous equation that you used to work with in conceptual physics was energy is equal to 1/2 mv squared. And if you kind of look at the units of energy, well, we always said mass was in kilograms. The velocity is meters per second, but because it's squared and squared here. You got choices in this classroom. I'm perfectly fine. You go either way you want. When you're solving and you're telling me that, hey, you know what? I got 1 kilograms meter squared second squared. Or you can say, you know what? I don't want to write all that down. I'm just going to say a joule. Because what a joule stands for is it's simply a shorter way of representing all these units. Oh, I got 2 kilograms meter squared second. No, I got 2 joules here. If you wrote it down with these units right here, not taking out any points because that's technically correct. But once again, we like to abbreviate it by going with joules here. And this class, which you didn't really use in conceptual physics, is this other unit that we use to represent energy and heat, and that's going to be calories. And when it comes to these calories, the calorie is going to be abbreviated CAL. Do not confuse this with the food calorie. It is not the same calories that you talk about when, hey, I'm going to go run and burn off 10 calories. Not the same. It's not the same calories when you look at the box of, I don't know, your Oreo cookies and it says 1 Oreo cookie is 200 calories. Not the same calories. Today we'll look at it and kind of look at how the calories we're going to work with in this class are different from the food calorie. And there is a difference there. Now, what's going to happen in this class is going to be just like how we did in the gas law chapter. In the gas law chapter, I say, hey, you know, what's the pressure in ATM? Or what's the pressure in millimeters of mercury? And you would just convert back and forth. Well, in this class, for this chapter, you're going to either give me energy in calories, or you're going to give it to me in joules. And you have an equivalent statement that's going to allow you to go back and forth in this case. So, once again, one problem might say, hey, joules, one might say calories. Just convert it in this case. All right, now we are finally ready to look at heat and understand exactly what heat happens to be. Yes?
Are we memorizing the...
You are, but don't worry about it. Like right now, 1 ATM is equal to how many millimeters of mercury? You worked with it so much, it's like ingrained in your head. You're going to solve so many problems that by the time you get around to the test, you are going to know this. Now, one thing to point out is I do, for these tests, make you kind of know this stuff. But when it comes to the semester exam, I'll be inclined to actually give you what the AP students get. And what the AP students get for every single test that they take. And this is because College Board realized there's a whole bunch of different things they're working with. They give the ideal gas law constant on here. They give them 1 ATM is equal to 760 millimeters of mercury. They tell them that 1 cal is equal to 4.184 joules. Oh, look at this thing, it's beautiful. Look, wait. Look, what law is that right there? This one right here. Combined gas law. I see perv nerd right there, PV equals nRT. I know, you never heard that term before. Some people call it that. But you'll see like all the different equations that are sitting here. The only reason they allow this for the AP students is because when they take that AP exam, it is harder than a college exam. Why is it harder? Because in college, what you end up doing is you take 2 semesters. Semester 1, you will take with a given professor. And that professor will say, we're going to stop at this point and moment in time. You take your exam, you're done. Come second semester, some of the material kind of carries over, and not all of it. Because that second professor who's teaching you, he can't guarantee exactly what was taught in the first, but he knows what you should kind of know. Which means the second semester is only over that second semester material. For those students who are going to like the AP chemistries, the AP biologies, or the BC calculus, you're being tested over a year's worth of equations. and constants and all that good stuff, and there's no way you're going to remember every bit of it. Now, I'll tell you, for my class, those AP students, they know the ideal gas law equation. They just know it like the back of their hands. You work with it so much. They know what R is going to be. But if they don't, they can look here. One of the reasons why I kind of do this, and I make you learn the equations, those who do come with me, when it comes time for the AP exam in May and you're rushing through, do you want to have to say, well, this is the ideal gas law, I know it, but let me go find the equation for it. It's PV equals nRT. What is the R? Let me find it on the equation. Oh, R is right there. It's so much quicker if you already know the equation. You are going to actually now have more time to go back and kind of look over and make sure that you're comfortable with the material. All right, let's continue on. Enough about that stuff. Heat, what is the difference between heat? Heat, if we look at it, is simply defined as energy that is transferring from one object to another because the two objects have a different temperature. So, let's go with the following scenario. Let's say that we were to take our hand and we placed our hand in some nice cold snow. The question I have for you is, would energy transfer from your hand into the snow, or would it go from the snow to your hand in this case? Hand to the snow. Because one of the things that we know is energy is always going to transfer from that object that is hotter to the one that happens to be colder. That's why you'll notice here with the coffee. The coffee, of course, is hot, and we can see that the energy is flowing out to the cooler atmosphere that's outside of it. Just like over here, we've got this delicious sundae. I don't know about you, when I look at this sundae, it just makes me want to go to Cold Stone and just say, hey, can I get some sherbet? Add a cherry to it, some celery, some olives, and all that good stuff to make this thing nice and delicious. But if we look at it, one of the things that I know is that thing is cold, which means that the air in this case, in this scenario, is going to lose heat, and the ice cream or the sundae is going to start warming up. So what we're looking at here is, once again, you've got to have a difference in temperature. And we can even explain what is going on here. For instance, if you take your hand, so everybody, take your right hand. And if you don't know which hand is your right hand, how do you figure it out? You do? I never knew that.
Yeah, the left is an L and then the other one is a backwards.
I learn something new every day. I didn't do that. What I used to do is I used to always think about Pledge of Allegiance. I just think about which hand I always kind of put over. Oh, that's my right hand. When I was younger.
I was under.
I
think about which hand I right with. No,
Well, you go that way too. You say which hand. I know that. Hey, my mom told me I was right-handed, and I'm right with that one, so that's my right hand.
Mr. Harrelson,
Yes.
you can hit this while you're driving too.
Yeah,
It's
that's
just
what
like, oh, this
I do
is
that
just
so
like,
much.
I don't turn left here, and I'm like, okay.
Are you really? So as you're driving, you're like,
my mom would be like, turn left.
I
I feel bad. I mean, like you say, Mr. Harrelson, what's right? Where's that way? Which way is left? You should not be at this stage of age. Think about it. Some of you are in this class. You're taking like all this higher level mathematics. Some students in here are taking calculus, and you still gotta do this to figure out right left. I feel bad. I'm sorry. I didn't mean to shame you. That was bad. That was bad of me to shame you by saying that. But I was like, come on.
Mr. Harrelson, you just said we have so much content we gotta learn, like so many other things we gotta know, that it's good to have a little cheat
All right,
sheet
you're right.
sometimes.
I agree. Because I do say that all the time. You got a lot of stuff to commit to memory, so we got a little trick to get around it. Okay, here we go. Let's get back to this problem we're looking at here. Take your right hand. Do whatever you need to do. L's, this, over heart, whatever. Take your right hand. You'll take your right hand, you'll place it on the table. When you place it on the table, you're going to tell me the table actually feels hot? Cold, okay. So it feels cold in this case. All right, which means that energy is flowing from where to where? Hand to table. Okay, so I know the energy is flowing from the hand to the table in this case. So watch what's going to happen here. If we think about the temperatures, the hand is going to end up being hotter or colder than the table? Hotter. All right, so what I want you to do is I want you to take your right hand. Right. This one's hotter. And if you think about it, your hand is kind of made out of, it's a solid, right? Which means the sort of motion it's going to end up having is what? Solids have what sort of motion? They vibrate, exactly. So they're vibrating. So you're going to take your hand, and this represents your hand. The right hand is representing your hand. You're going to make it vibrate back and forth pretty fast here. All right, we got that. Here comes the tricky part. The other hand is going to represent the molecules of the table. And the table molecules are going to be moving how? Slower. So this hand needs to move fast, and you need to take the other hand and make it move. It's tricky. It's tricky. So this one's fast, the other one's slower. But think about it this way. I see some of you doing like this now. But fast and slow. It's tricky. It's like trying to get the two like hemispheres of your brain to kind of work together. And once again, each hemisphere is working the other. Anyway, if you think about it, the fast-moving molecule, I'm going to bring them in contact with each other. So this one's fast, this one's slow. When the fast-moving molecule hits the slower-moving molecule, what's going to happen to the faster-moving molecule? It's going to slow down. And if you think about it, this kinetic energy is the temperature, isn't it? Which means that if this faster-moving molecule, which represents our hand, hits the slower one, it starts to slow down, then the temperature of our hand absolutely is going to feel colder because the molecules are moving slower in that case, right? But if you think about the table, if the table is moving slower, my hand is moving faster, when that fast-moving particle hits the slow-moving one, what's going to happen to the slow one? It's going to speed up. And eventually, over time, what's going to happen between the two? They're going to get like this to each other. And we're going to have like a thermal equilibrium where they're going to reach that final kind of destination as far as their temperature. So even if we think about it on a microscopic level, we can see exactly what's actually going on. And if you could zoom in and you could see the actual molecules, you would see the molecules kind of colliding and hitting each other, and one speeding up and one is slowing down in this case. But in order to get, once again, to have a temperature, because then if you think about it, once we do reach thermal equilibrium, guess what we don't have anymore? We don't have heat anymore. There's no more transfer of energy. You can only have heat if you have the two objects at different temperatures. That's why when it comes to, hey, I'm feeling feverish, I need to call who? No, you don't call it doctor. You don't get on the phone to call it doctor. Who do you call?
You call your mom.
Oh, man. My last class said I need to seek therapy because I asked the same question. And they were like, oh, Mom.
Oh, why don't you call your dad?
Why don't you call your dad? We're there too in the house. Also, if you think about it, this is where it gets bad. Listen to this. And then you're going to say, yeah, Mr. Earl, you need to seek therapy. If you think about it, you see, yeah, therapy, because this has always bothered me as a dad. I'm like, why can't you call me? I'm here. I know how to put up the thermometer. Look, I can do it too. You know? But anyways, let's get on this way. Listen to this. Whenever you have like somebody who's like taking the stage and they're presented with an award, who is the person they thank first? Their mom. I'm like, son, I was out there passing and throwing the football. And you can't even acknowledge me? It's always, I would like to thank my mom for being there. Like, what are you talking about here?
God gives things first.
Did you birth a child?
Did I what?
Did you birth a child?
I did not, but I still had a hand, and also I had a hand in like teaching them how to catch. And all right, anyways, all right, enough about me. Maybe I do need a therapy here. But once again, I just want you to realize us dads have feelings too. Call on us every so often. We know how to work thermometers. All right, back to this thing here. Once again, when it comes to having a temperature, we don't put our hands on our forehead because the problem is that a lot of times our hand and the forehead have to be the same temperature. And you're not going to be able to tell that you have a cold. But at the same time, if you have a parent who comes in and they put their hand on your forehead, then all of a sudden they're going to say, you feel how? Hot. Because that's the energy flowing from your forehead into their hand, and it's causing their hand molecules to start vibrating faster. And once again, they're feeling, once again, this increase in temperature. Yes?
I have a question. But when you have a fever, you know how like, not like to the touch, but like you feel cold. Why do you feel cold?
Ooh, very good question. Because guess what your body is doing to the atmosphere?
It's like,
It's sending
You're
heat to the
losing
atmosphere.
heat to the atmosphere, right?
yeah.
And if the energy is flowing out of you, what's happening to your overall energy in this case? It's going down, isn't it?
Yeah.
Hence, I'm feeling cold. And one thing just to point out, and then I gotta get back because I'm going to go off on a tangent really quickly, is the body is an amazing thing, whether you realize it or not. Think about it. If we get forget the fever for 1 second. When are you most prone to come down with the flu? When it's cold, right? Okay. I catch the flu. My body, for some reason, likes to warm up
Bacteria dies.
because things such as viruses do not like warm environments. That's why you're less inclined to catch the flu during the summer. And that's why the body is doing, once again, it's an amazing thing. It's like, hey, you know what? I find something foreign in here. I'm gonna make it really uncomfortable by making the temperature of the body actually go up. Now, of course, a lot of times your doctor will tell you, hey, if they have a low-grade fever, don't give them anything. That's their body fighting. They're trying to elevate the temperature to, once again, make the virus where it will not replicate at a fast enough rate. And eventually your bodies will build up the actual antigens and so forth that get in there and actually fight it. But once again, having low-grade fever is something that's fine. Yes.
This is kind of unrelated, but like, how does the temperature change so fast sometimes? Like, how was it 80 degrees yesterday and now it's like snowing?
Let's talk about that right afterwards. Let me just make it through the notes, but if you want to stay right after in a lunch, I can absolutely talk to you about it. Yes?
Okay, then how do you get cold though? Like sometimes your temperature goes down a lot.
Oh, we're talking about it. We'll get it. Give me a second. All right, here we go. Let's just talk really quickly the difference between, once again, temperature and heat. All right, I got two thermometers right here. And this object, once again, clearly is some warmer atmosphere, and it said, hey, we're at 60 degrees Celsius. This thermometer is in some colder atmosphere, it's at 30 degrees Celsius. And remember, we said that when it comes to temperature, temperature is a measurement of average kinetic energy, which means that if I go from 30 degrees Celsius to 60 degrees Celsius, that implies, since we're ready for the test tomorrow, that implies that the actual kinetic energy doubles. So we went from 30 degrees Celsius to 60 degrees Celsius.
No.
No? Because it's got to be in kelvins. You're 100% correct. If you add 273 and 273, that's not a doubling. If this was 60 kelvins, and that was 30 kelvins, that would absolutely, it's doubling, in this case, the actual kinetic energy. Some of you are definitely ready here. So if we look at temperature, measurement of average kinetic energy, heat, is now when I take this hot thermometer and bring it next to this colder object, and I push the two together, then energy clearly is going to flow from that thing which is hot into the thing that is cold, and I can say absolutely we've got heat in this case, and we got our energy transfer. All right, next thing we talk about is we need to talk about this thing known as the system and the surrounding. A lot of times when we study the flow of energy, we need to really define those two things. And it's pretty easy to define. The system is going to be wherever we focus our attention on in this case. The surrounding is going to be everything outside the system. So, for instance, in my mailbox, I have no idea why, but for some reason, this was placed in a lot of our faculty members' mailbox. I don't know why, but somebody used to be like lotion sunscreen or something. I don't know if they're saying like, hey, faculty members, your skin look a little dry, we're gonna give this to you, but everybody's mailbox had this in there.
It says vacation on it.
It says what?
Vacation. They want a vacation.
Oh, maybe, okay, they're telling me I need to go on vacation in this case. All right, I got this right now. If we are all focused here, I can say you are my system in this case. And then once again, everything outside the system is gonna constitute, in this case, the surrounding. And if I have the system and everything outside of it happens to be the surrounding, then that means that we have the universe. Because that's everything. All right. Kendall, what are you doing back there? Everybody look at Kendall. Everybody look at Kendall. Look at her. What are you doing back there? Okay. What is Kendall right now? She has a little red. I grant you, I feel terrible. She's our system. She's my advisor, so I can do this. So she knows it. I mean, come on. Have I ever called anybody out of class in the middle class?
Yes, me multiple times.
No, I haven't called you out in the middle. Like, I might say, Kendall, give me an answer. No, I never said that. You offer answer.
You're not confident in your answer. Everybody at NASA is gonna die if you keep out.
Oh, I don't say NASA's gonna. I just say that you gotta be confident. You're gonna be my, once again, you are gonna be my aerospace engineer, right? I gotta build and make sure you have the confidence. I don't want that astronaut to go up on that space shuttle and be like, are you, how's this looking? I think it looks like it's gonna be okay. I need that confidence. You gotta reassure the astronaut that, hey, you are going to be safe. I made sure I looked at my significant figures and everything else. All right, here we go. Kendall, how do you feel right now? Hot or cold?
It feels like this is, I don't know, like it's kind of hot in here now.
You feel kind of hot. So Kendall feels hot right now. All right, if we think about Kendall as being our system, if she is feeling hot, is she taking energy in, or is the energy flowing out of Kendall? She's feeling hot.
Out.
She's taking it in.
She's taking it in. Because if she's taking it in, then the energy is growing within her, and she's gonna be like, whoa, I feel hot in this case. So what we can do is we can say that the system is gaining or losing heat. She's gaining, right? Kendall is gaining because she's a system.
But it's cold and I'm ruining my body.
Hold on one second. If she is gaining, then what can we say about the actual surrounding? The surrounding is losing in this case, right? And if we think about the universe, has the universe gained or lost any energy? No. Because one of the things that we're going to see is that for every physical or chemical process, the energy is either going to flow into the system, that means the surrounding is losing the energy, or it's going to flow out of the system, which means the surrounding is going to gain the energy. But all energy must be accounted for. So we got our system, wherever we focus our attention, we got the surrounding, which is going to be outside of it. And this example right here, it kind of shows the exact same thing. It just simply says that, hey, you know what? Maybe we got something with some initial amount of energy, such as, I don't know, this lotion right here. Even when I look at it, I can say, hey, lotion, let's see. Oh, look. It just went down to where? To ground, which means it has what as far as its energy? Lower what? Potential energy. It just lost energy in this case. Here, if we look at it, when things lose energy, so hey, something's got a lot of energy, it goes down to a lower energy. The energy that's being lost by the system, once again, has to be gained by somebody. It's going to be the surrounding. Just like the converse. If I have somebody low in energy, and if I increase its energy, then it had to take energy in this case, which means that's growing in energy. I can say the system is gaining, and the surrounding in this case is going to end up losing in this case, which is going to bring us to this terminology right here, which simply says that when it comes to either a chemical reaction or a phase change, and a phase change is like boiling, freezing, what else we get? Condensation, things along that, just where it's changing from one state to another. There is always some amount of energy that's either being lost or gained. Now in chemistry, if something is taking energy in, we say that it's a endo. Endo means to take in, thermic means heat, so it's absorbing heat in this case. If we have what is called exothermic, exo to exhale to release. So exothermic implies that you are losing energy in this case. And when you go into biology next year, you're going to be using this term, exothermic, endothermic. Sometimes they use exogamic or endogamic. It means the exact same thing. So here we go. If a process happens to be endothermic, it's going to feel cold. This one I got to go over with you. Even the AP, they still, for some reason, have a little bit of difficulties with this, but it's really easy. If you look at it, a lot of times we are going to have to be the individual to kind of figure out whether or not something is losing heat or gaining heat. So let's just say that we have the following here. That's pretty good, not bad. It's a piece of ice. And then let's say we have the following. We got somebody's hand here. So that's her hand.
That's a lot of fingers.
Don't be finger shaming this individual. They got their hand in. All right. They're going to take their hand and they're going to touch the ice. I don't want to do that part. So they're going to touch the ice. The question I have is which way is the energy going to flow? Is it going to flow from the hand to the ice to the ice to the hand?
Hand to the ice.
Okay, so we can clearly see it's going to go like this, right? Is that snow?
Yeah.
Yeah. It's been
Oh my God.
It's been snowing.
It was just 83 degrees outside
That's what we're
yesterday.
I swear
You
nothing's
can't have
real
snow the
anymore.
next
We're living in the
day.
Matrix. This isn't
That's
right.
what Adrian asked you. And you didn't
I thought it was like raindrops. I'm like, you know, my eyes are deceiving me. That's just raindrops. That's snow. Oh my gosh. Okay, here we go. Let's continue on. We got to make it through these notes. All right, so what we got going on here? Is the ice we can say is going to be endothermic or exothermic? It's endothermic. So I'm going to say the ice is endothermic. So the ice is endothermic. But if you think about it, when I go and I touch the ice, my hand is going to end up being what?
Cold.
Cold.
Exactly, which means that it's going to be what? Hand is. Energy's flowing out of the hand. It is what? Exothermic. Because it's exiting out of the hand. Exactly. Exo, to exhale, to exit, all means to flow outwards in this case. So the only thing I want to point out is that when I go and I want to figure out if something is endothermic or exothermic, it's going to be just the opposite to me. Hey, my hand is getting, in this case, colder. Which means heat is flowing out, which means whatever I was just touching has to be the thing taking it in. You're going to be endothermic in this case. Just like if I was to do something like this right here. So here we go.
Is that a beginning of a fire? Oh no. Is it a foot?
Why are the toes so spiky?
Is it a flame? Oh my
All right,
god.
what is this going to be right here?
Fire.
Fire.
It's a fire.
It looks like a band-aid.
No, it's not a Band-Aid. What is that? Come
It's
on.
fire.
It's a fire, but what do we call this normally?
A
You see this?
campfire.
It's a campfire, exactly. So it's a campfire. So we got the logs there with the fire coming up. And that, of course, is going to end up being a foot, right?
Hey, he has 5
Because everybody's always sick your foot. You stick it up by the campfire to warm it up. I don't know why we do that, but it's just kind of cool thing to do. All right, if we look at it, heat's flowing which way?
From the fire to
Fire
the
to
foot.
the foot.
Okay. Which means that this process right here, the flame, is going to be exothermic or endothermic. Which means that, of course, our foot is going to be endothermic. Exactly. So basically what's going on is it's like the opposite. So whatever that object is doing, so if our hand is like, oh, I'm losing heat, that means that must be endothermic. Oh, my hand is gaining heat. Okay, well, that means my hand is endo. That must be exothermic here. So just keep that in mind. And that's what it says right here. Endothermic processes are going to feel cold, while exothermic processes are going to feel, in this case, to us, hot in this case. Because we are the ones who will need to detect whether something is endo or exothermic in this case. Yes.
So I was just confirmed, when you say it feels hot, you mean like when you're touching it, it feels hot, not like it itself, like to it. I mean, it's a flame, so it doesn't feel anything. But if it was a flame, it would feel hot.
It would feel hot, exactly. So I don't even really have to touch it. I can have my hand close to it.
No, yeah.
And it's still going to kind of flow in this case
Okay.
as well. But yeah, we're just looking at touching and kind of figuring out whether something is endo or exothermic. All right, I'm going to go to this slide right here. Things that are endothermic. I can clearly see that this is an endothermic process because the energy is flowing into the system. So the system is growing with energy. And once again, this endothermic, like I said, the surrounding is going to end up being exothermic in this case. Now, one of the things to keep in mind is if you remember, when it comes to heat, the symbol that we use to represent heat is going to be the symbol Q. So Q is synonymous, or the symbol that we use to represent heat. Got you. So if you look at what we're going to do here, I can say, hey, you know what? The system, the heat of the system. Now, one of the things that we're going to start doing here is we're going to start using like positive and negatives. And you got to understand what that positive means. It's not the same as like a negative number or a positive number. It just simply tells me what in the world is going on with the system. And if I look at it, it says the system is gaining heat. Or you can say the system is increasing with heat. That's all the plus simply means, to gain. Just like we're going to see in the next slide, where we're looking at something that's exothermic. You're going to see that if it's exothermic, then hey, the energy is flowing out of the system. That's exactly what this says. It says the system is losing heat. The negative simply means that you're going to lose. Because if you think about it, if I tell you that I have some energy, and the energy happens to be 100 joules, and positive 100, all this simply says is that, hey, you know what? That's the energy that's flowing into it. But if somebody told me, hey, you know, I got something completely different, and it happens to be something like negative 100 joules, then I'm going to say, you know what? There is no such thing as negative energy. You can't create nor destroy it. All the simply thing that the negative means is that this means that we are going to have a loss. This means that we are going to have a gain. We are gaining that amount of heat. This is losing 100 joules of heat. And a lot of times in this class, especially with this chapter, you'll see positive and negatives. That's all the positive and negatives mean. Because one is losing, one is gaining. It's kind of our way of kind of handling, telling who's going to gain versus who's going to lose. All right, that brings us to right here. Let's just say our universe was made up of an ice cube and some warm soda. And let's just say that I took, in this case, my ice cube and I plopped it into the warm soda. Then I know exactly what in the world is going to go on here. I know that the warm soda is going to transfer its energy into the ice cube, right?
Right.
So I can say that the Q of the soda, and if I think about the Q of the soda, would it be negative or positive? Negative, okay. And if I think about the Q of the ice is like, hey, look at me, I'm taking energy. It's gonna end up being positive here. And this says pretty much everything. Soda losing heat. Ice is gaining heat. That's all it says. But one thing that I know is that technically, I can do something with these two things right here. What can I possibly do?
You can set them equal to each other.
Let me see if that reads correctly. Heat lost by the soda equals the heat gained by the ice. Seems to work for me. You can set the two equal to each other. And this is going to be an equation that we're going to see on the next page, where it's going to simply say that if you bring two objects together, we'll get there in 1 second, it's going to say it is imperative for you to use this equation right here. Because we have a test tomorrow, on Monday, we're going to start going through some problems. We're going to start solving problems. We're going to come across this problem, and it's going to look like it's impossible to solve. But then one person in his classroom is going to say, wait a second, we're taking two objects at different temperatures, we're bringing them together and in contact with each other. Hey, Mr. Harrelson, what if we use this? And when we use this, and don't get me wrong, what's inside the Q is going to grow. There's a whole bunch of things you got to calculate to get to the Q. It's going to make the problem just kind of, what would be a good way of saying it? It's just going to melt in this case, just like the ice cube. It's going to become extremely easy. But it's going to be imperative that you must use that equation here. All right, going through this last slide, we got 1 minute here. So once again, we already said that once again, we can define the Q of the ice as being positive. We said the Q of the soda is negative, which brings us to, once again, this exact same expression we have here, we have on the board, and then we just simply said it right here. Anytime we bring two objects together that have different temperatures, we are going to absolutely use this equation here. All right, that is it for today. And the only homework you have tonight is say, Dad, can you please take my temperature? Even though you don't have a cold, but just make him feel like he's a part of your family. Ask him that good question.